So, good morning, all of you. Myself, Fanil Patel, uh, from SOPAN Infotech. So, I am an application engineer at SOPAN Infotech, and so what we are doing, what SOPAN doing, and what is SOPAN. So, just look at the small brief about it. So, SOPAN Infotech is a authorized reseller for CAD, CAM, and CAE products. So for CAD and CAE, we are channel partner of Dassault system, and for CAM, we are channel partner of Hexagon. Okay. So in Dassault system, we have three products. First is SolidWorks 3D CAD solution, in which we provide CAD solution. Then a second product is draft site, in which we provide a 2D CAD solution. So any 2D drawing, something you want to draw. And at last, the 3D experience cloud connected platform. So this is the basically a platform to collaborate the business solution. Okay, so that is 3D experience works. In Hexagon, we have another three products. First is Esprit Cam. So in Esprit Cam, you can generate NC CNC code for your machine from 2 axis to 22 axis. Then we have product called Radar. So if you are from sheet metal industry, so if you are dealing with bending or sheet metal cutting industry, then we have Radar. And VZ is a CAD CAM solution for die and mold manufacturing. So this is the overview of SOPAN Infotech. Okay. So let's jump to our today's webinar topic. So our topic of the day is SolidWorks simulation for everyone. So before going to the topic, let me clear what is simulation. So when we are designing any CAD design, okay, so it is necessary to validate that our design is good enough or not before we are introduced into actual problem. So if we do not do that, then what happen is that in actual scenario, the product may get failed, or a worse scenario could happen. Suppose I am designing a bar for my bridge. Okay. So suppose I have designed it randomly, I do not perform any test, and then when I'm going to implement that, so then the contractor will ask me to perform or validate that your design is correct or not. So what we are going to do is we are going for experimental approach. So in experimental approach, there are many iterations you are going to perform. Suppose you have designed one I section beam. Okay, so suppose in particular loading condition that beam is going to fail. So what you are going to do is you are going to change the profile and doing some another iteration. So safer your design. Okay, so this iteration will take a lot of money. So to eliminate that cost, we have performed simulation. Okay, so SolidWorks provide simulation scenarios for different domains. We basically follow FEA module, that is finite element method, and in FEA module we are going to study which domain we are going to cover today. Okay. So in our today's agenda, we are deep dive in the different SolidWorks analysis that are available in SolidWorks simulation. Okay, so let's start with first our static analysis. So what is static analysis? Static analysis means static means independent of time. That is the that your product or your load you are applying on your product, that does not depend on time. Okay, so that is called static analysis. So static analysis allows you the time invariant calculation for displacement, stress and strain in one single body or multi-body parts. Okay, so the results are consequently of the applied constraint and loads, for example, bearing, gravity, force, pressure, etc. Okay, so what does it mean? Okay, suppose I have this flange. Okay, so I want to design this flange that this flange is fixed here. Okay, I just show you. Okay, so my flange is fixed at this point, this point, this point, and another one hole at the back side. Okay, and I'm going to apply a torque to this part. Okay, so I want to validate that how my product is going to behave. Okay, or whether my product is safe or not. So if I want to check that, so I will perform a static analysis in SolidWorks. Okay, here my torque value does not depend on time. Okay, so that I can go for static analysis. So when I perform this analysis, so here you can see the result. Here you can see that how this product going to be behave under the torque. Okay, so this shows a color diagram. So when you are doing so, so you see the red portion, which suggests that at this region your part may got fail if it is a high extensive load. Okay, so this is how you can perform static analysis. So static analysis also covered three sub parameters, that is called solid body analysis, cell body analysis, and the last one is beam analysis. So what is solid body, cell body, and beam analysis? So first we looked a solid body analysis. As we see here, if you are making a part by a 3D CAD model, like just like extrude or revolve or other features. So in that case, we are going to perform solid analysis. So this is about solid body analysis. Suppose we go for cell body analysis. So what is cell body analysis? If our part is made of sheet metal, suppose we made this flange, this sheet metal part with a sheet metal feature. Okay, so to perform this study, so in FEA, we are doing meshing. So generally the sheet metal thickness is around 2 to 3 mm. Okay. So if I want to accurately capture the phenomena, so I may got to fix minimum 2 to 3 element at that thickness. Okay. So if I going to apply that small amount of thickness, so it may get that my computational time will be very large. Okay, suppose this flange is thickness is 2 mm. Okay, and the entire length is about 100 mm, 1000 mm. Okay, so for better capture, I need to need to fit minimum 2 element here. Okay, so to fit 2 element here, my element size should be 1 mm. Okay, so think of it 1 mm element size for 1000 mm length. Okay, so what amount of mesh we are going to generate? So it basically took a very long time for meshing, then for solution, and it may be that it will also corrupt in between. Okay, so to remove this, SolidWorks introduced Cell Manager. So what is Cell Manager? So Cell Manager is a feature of cell body analysis in which if our body is generated by sheet metal or any surface feature, so SolidWorks automatically convert that body into a zero thickness surface. Here you can see a zero thickness surface is generated. Okay. So what we are going to do is simply mesh this surface only. Software automatically find this thickness and perform the consequences analysis accordingly. Okay. So this is the main advantage of solid body analysis. So here I have performed one analysis. So here you can see. I have fixed my part here and I applied a pressure here. So how my body is going to perform? Uh, so here you can see. And also the computational time for this body is very minimal. Okay. So this is a very big advantage why we are using SolidWorks simulation. So we have cell body analysis. Then we have beam analysis. So what is beam analysis? Suppose I want to measure one beam which is subjected to different loads, suppose point load, UDL load and different types of load. Okay. So now I want to check that whether my beam is going to sustain that load or not. Okay. So same like sheet metal, beam is also small thickness. Okay, suppose this is my I section. So the thickness of this I section is around 1 mm. Okay, and the overall length is around 100 mm. Okay, so suppose you are going to fail minimum 2 mesh element on that thickness, then your mesh size will be 0.5 mm. Okay, so zero point 0.5 mm will be very critical for you because to fix that 0.5 mm element over 100 mm length, it is very tedious job. Okay, so what SolidWorks have solution for this is SolidWorks just simply, here you can see, just simply divide the entire beam length into small segments. Here you can see. Okay. So what we are going to do is we just going to perform one simulation for that part. Okay. Then automatically this result will be carried to this part and so on. So this is one best solution for any industry who are dealing with beam design or beam analysis. Okay. So not only this, if we want to capture shear force or bending moment diagram for a beam, so we can easily derive from the simulation. So here I have one example. So here you can see a beam is subjected to two different load. First is UDL, that is universally distributed load, and second one is a point load. Okay, so here you can see my beam is fixed at this point, and here I have provide roller connect. Okay, so different types of connects also you can apply. Okay, so if you want to apply fixed geometry, okay, or roller connect or any connection you can apply here. Okay, so how my body going to be perform, or how my shear force and bending moment diagram are. So here my shear force diagram and my bending moment diagram. Okay, so it is very easy to capture this phenomena. So this is all about static simulation. In static simulation, you can perform single body simulation or multi body simulation on a solid body, cell body, and the beam analysis. Okay. So then we jump to our next topic, that is buckling. So what do you mean by buckling? So uh, we have performed this experimental when we are in our school time. Okay, suppose we have our ruler, plastic ruler. Okay, generally 15 centimeter ruler. So what we are doing is we just fix this ruler here and apply load here. Okay, so what happen is my ruler is going to bend like this. Okay, so this bending is nothing but buckling. Okay, and this is only happen when your body is a slender body, that means thin body, or your body is under the compressive load. In tensile load, buckling is not the case. Okay, so when we are designing beam, so this is the main problem after the static analysis, that is buckling. Okay, so suppose I have designed one beam and the cross section area is very small, or suppose I have designed one column Okay, and the column cross section is very thin, and I have applied the load, so my body is going to be bent. So I want to check whether my body is going to bend or not, or what is my factor of safety for that compressive load. So that thing you can perform in buckling analysis. So buckling analysis follows the Euler's column formula, that uh, is going to perform the Euler's formula, that is P critical, that is our critical load, is equal to pi square EI upon LE square. Okay. So you can also cross verify that that the software value and your theoretical value is going to match for simple case. But if you are going to very complex shape, then you don't go for theoretical approach. So you either go for experimental or simulation. So before going to experimental, we suggest that you go with simulation first. Okay. So here I have one example. So this is my beam column, sorry, this is my column, which is fixed here and subjected to a compressive load here. Okay. So I want to check how my beam is going to perform. Okay. So here you can see. So this is how the deflection phenomena is captured in SolidWorks. And also you can get the factor of safety graph. Okay, so what is your factor of safety for this corresponding load? Okay, so here we have factor of safety of 1.155. Okay, so we need to look at that. We need to decrease our load or we need to increase our thickness, because 1.55 is a very critical value. So for safe design, our factor of safety must be between 2 or 3. Okay, so it is nearer to 1.55. So software automatically suggests that you don't go for this iteration. Either you increase your thickness or decrease your load. Okay, so depending upon your corresponding data, that you can either decrease your load or increase your thickness. Okay, so this check I can get from the simulation software. Suppose if I don't use this software, then what I'm going to do is, first I'm going to build this beam, go for an experimental analysis, and this beam is around 2 meter height. Okay, so just think about the cost. Okay, and this beam is going to fail. From result I can capture. Okay, so this is very difficult for any industry, that you cannot spend that amount of money to uh, make one beam and then go for second iteration up till your beam going to be safe. Okay, so that iteration is eliminated by this simulation software. Okay, so this is about beam. Then we move for our next topic, that is a pressure vessel analysis. Okay, so what is the pressure vessel analysis? So generally, when we are designing pressure vessels, so pressure vessel is a very critical part in any industry. Either you use it as at a boiler or use at is at uh, pressure tank, which provide high pressure air whenever you require. So the container which store that high pressure air must be strong enough. Okay, so to perform that analysis, SolidWorks has a different module called pressure vessel analysis. Okay, so what here we are going to do is, we going to implement different types of studies. Okay, so suppose I have one weight analysis. Okay, then I have one temperature analysis, one pressure analysis. So I can combine that multiple analysis, and all combined analysis I can import it to my pressure vessel body. Okay, so here I have one example. So you can show. Okay, so this is my pressure vessel. Okay, so I have applied multiple loads, and this software shows me how my body is going to deflect. Okay, so here I can see my deflection. Okay, so similar way I can also predict how the stresses are going to produce in the body. Okay, so here you can see what are the region which are under high pressure. Okay, so this analysis is done in SolidWorks. Then next analysis is optimization. So I can say this is the biggest advantage of SolidWorks simulation, that it is an integrated part of CAD design. Okay, so if any change in CAD, uh, automatically revert back to simulation, and any changes are suggested by simulation software automatically reverted to CAD design. Okay, so this is the best example. Suppose I have one knuckle. Okay, so here my knuckle is. So what I'm doing is I am just apply. I can show you. So I am just apply one torque here. Okay. So you can consider is that cap of any container or any tank. Okay. So this is like a cap. Okay. So I'm going to apply torque here, and I'm want to find that whether my part is safe or not. Okay. So that is that analysis we done in static simulation. Okay. So these are the result of static simulation. Okay. But now here you can see my factor of safety is around 5.87 into the 10 raised to power 3. That is, the factor of safety value is 5878. Okay. So here you can see that my part is uh, highly secure. Okay. So now what my challenge is, I want to reduce my part thickness or my part mass. Okay. So what I'm going to do is I'm going to perform an optimization analysis. Okay. So what optimization do is it simply take you from the various variables. Okay. Suppose you define that my this parameter has this limit. Okay. Suppose I show you. Suppose this is my part. Okay. So I want to check that this thickness, rib thickness, is this has some limit. Okay. Then this whole diameter. Okay. So the here it is 2 mm. Okay. So I can reduce that. Also my outer dia and sorry, counter dia and depth. Okay. So this also I want to check that it is in safe condition, and if I can reduce or not. Okay. So to perform this, what I'm going to do is I just simply going to put this variable. Okay. So in cut diameter, I select that dimension and provide range. Okay. So I provide range that my value should be in between 2 mm to 9 mm. Okay. Then my height, that whole height. Okay. So that will be around 11 to 15 mm. The depth. Okay. So I have defined multiple parameters here, that this parameter I can vary. Okay. So in variables, I can enter the parameter which are going to variable. Okay. Then constraint. Constraint means here I have defined factor of safety, that my factor of safety, the minimum factor of safety, that does not below 2M. Okay. So here I have defined that condition that my factor of safety will be more than 2. Okay. And my goal, what is my ultimate goal for which I'm going to uh, optimize my model. So my goal is to reduce this mass. Okay. So to reduce this mass, so what software going to do is, software going to do multiple scenarios. Okay. So suppose that is one iteration, second iteration, third iteration. In that case, the software had going for 146 scenarios. Okay. So in 146 scenario, at 14 iteration, it found the correct value. So here you can see in green color. So what are these value? That my cut diameter should be 9. Okay, height should be 11 and other parameters. So software automatically reduce that model to optimized model. Okay. So here is my optimized model. So here you can see I have excessively defined my rib thickness. So software has decreased this rib thickness. Okay. Also this diameter and counter diameter also, what this height is also reduced. And here you can see in first case, my factor of safety is around 5878. Okay. Now my factor of safety is reduced to 3545. Okay. So here you can see how I have reduced my mass and still my product is safe. So if you have any product that is already safe, but you want to reduce this mass, or you want to check up to which limit I can go, so my product is going to save for the same loading. So for that, SolidWorks has optimization analysis. Okay. So here is my initial one product. Okay. And this is my final one. Okay. So here you can see what difference is we have achieved here. Okay. And also it is a parametric model. Okay. So if you want to change any design data at any stage, you can also perform. Okay. So optimization gives you a parametric model, but you have to give some variables that these are my properties which have this range. Okay. So this is about optimization. Then we have topology. Okay. So topology and optimization are both are similar, but only change is that topology gives you non-parametric output. Okay. So what is that? I can show you. So suppose I have, I am going to design one disk. Okay. So this is generally a disk break. Okay. So I want to design my disk. I have fixed my model here at this location. I have fixed my model. Okay. And I have applied a torque here. So in actual motion, the torque will be applied. So now I want to check that I want to reduce the mass of my model. Okay. So to perform this, I'm going to do topology analysis. Why I'm not going for optimization? Because in optimization, already I have told you, I need to define some parameters. Okay. That these parameters should be available. But here I have don't have that parameters. Okay. So when you don't have any parameters, but you still want to reduce your mass or for the same loading condition, so we are going to perform topology analysis. Okay. So in topology, as you can see, after the performance, here you can see that my final shape should be like this. Okay. And this area I can cut out. Okay. Here I have defined some preservative, that is this is going to be mount on my wheel. Okay. This hole going to be mount. So I have preserved that area. Also these bolts are mount. So I have preserved that area also. So which part you are going to preserve. So that is also you can define in the topology analysis. Okay. So this is my final model. So first my model is this. So after topology, you can see I can make this cutout and still my disk is safe for the same loading condition. Okay. But the only disadvantage is it is a non-parametric solid. So you need to design one product according to this. Okay. But similarly, you can export this model as step file. Okay. And from step file, you need to generate your output model. Okay. So this is about topology. Then we have drop test. Okay. So this for the electrical industry, it is a very big issue. Okay. That your product is fall from certain height. So whether my product is safe or not. Okay. So to check that, we have separate segment, that is drop test. Okay. Also, some industry are dealing with packaging. Okay. Suppose this is this example. This is my hard disk. It is packed between two foams. Okay. These are two foams with it is closely packed. Okay. And suppose my this packaging is dropped from certain height, and I want to check whether my body that is inside my packaging body, so it is safe or not. Okay. So to perform that analysis, we have drop test. So what we are going to in drop test is drop test basically used for impact loading. Okay, so suppose you drop some part from certain height, so there will be impact loading. Okay, so to analyze what is the impact and what is the corresponding effect to all parts, so to check that we are going to perform one drop test. Okay, so let's go for drop test of the electrical equipment. Okay, so in first case, okay, so here you can see this is how a drop test perform. Okay, so you can see that I have dropped this packaging from 3 meter height, and here you can see after the collision, okay, my bottom part is going to be separated. Okay, not only this, I have also put two sensors here. Okay, one sensor is here, I show you, one sensor is here and another sensor is here. Okay, so what is the effect of that point? Okay, that also you can capture here. Okay, so here you can see what amount of stress is going to be generated on that both parts. Okay, so for different time segment I can measure. Okay, so this is this is about drop test. Second, we are going to perform a drop test on a camera casing. Okay, so here you can see. Okay, and here I have defined multiple sensors. Okay, so suppose this is my clip which going to be joint my uppercase and lowercase. Okay, so I have defined 4 points. One is here, one is here, one is here, and one is here. Okay, so according to that, you can also define whether my body is going to be performed while or not. Okay, so this is about drop test. Okay, then we have frequency analysis. So why did frequency analysis? Okay, so as we see the static analysis and buckling and all that stuff that are not depending on time. Okay, but in actual condition, most of the cases are that your product is defining sorry, your product is going to be on any fluctuating load. Okay, so I want to check whether my body is going to sustain that load or not. So to perform that analysis, we have separate segment, that is frequency analysis and fatigue analysis. Okay, so first we do frequency analysis. So what is frequency analysis? So frequency analysis measure your resonance frequency. Okay, suppose I have one hook. Okay, here you can see I have one hook. Okay, so you can imagine in 10, 12 standard we perform this practical. Okay, in our school. So what we are going to do is we going to uh, fix the part from here, and we are going to snap this part here. Okay, so what is going to be done is that this body is going to be vibrated with certain frequency. Okay, so natural frequency or resonance frequency, the main difference is that when my body every body has its natural frequency. Okay, so if my excitement frequency is equal to my natural frequency, then my body is going to be vibrate very exponentially. Okay, so I can show you. Suppose this is my excitement frequency, and the natural frequency of my part is matched. Okay, so here you can see how violently it is going to be affect. Okay, so large displacement is going to be captured here. Okay, so to um, to find that whether my excitement frequency is equal to my natural frequency or not. So what we are going to do is we are going to perform a frequency analysis. Okay, so in frequency analysis you may find your natural frequency of whole assembly. Okay, for single part it is very easy to measure, but think of very large assembly or large machine. Okay, so in that case you need to go for computational side. Okay, so SolidWorks simulation has frequency analysis. In frequency analysis, software will automatically give you the natural frequency of any body. Okay, suppose this body has 390 hertz natural frequency. Okay, so when my external frequency is equal to 390 hertz, then it is going to be vibrate in this fashion. Okay, so uh, I just sorry, I have mismatch. Okay, okay, okay. Sorry for inconvenience. So this is how the frequency analysis is performed. Okay. So now we go for fatigue analysis. Okay. So this is one other example of frequency analysis that I have beam that is connected between two holders. Okay. So from this side I have one excitement load. Okay, so how it going to be affect the holder? So here you can see. Okay, so this is how frequency analysis works. So next we go for fatigue analysis. Okay, so what is fatigue analysis? Okay, suppose I have one key here. Okay, so what I'm going to do is I'm going to apply 100 Newton load here. Okay, and I want to check and fix here. Now I want to check that whether my this body is safe or not. Okay. So in static analysis, you can easily predict that my this part is safe. Okay. So here I have performed the static analysis. So here you can see the factor of safety, minimum factor of safety is around 41. Okay. So my part is safe at 100 Newton. Okay, if I applying a gradual load without that is my load does not vary with time. Okay, so from this study I can predict that my body is safe. Okay, but in actual condition my body is subject to a cyclic load. Okay, so what type of cycle is performed is, so here I can show you that suppose my body is subjected to 100 load, 100 Newton load, then comes down to zero. Again 100 comes down to zero. Again 100 comes down to zero. Okay. So I have loading like in this fashion. Okay. So in static analysis, I cannot perform this study. So to study this, I need to go for a fatigue analysis. Okay. So for fatigue analysis, when you are designing any model for your fatigue design, okay, then your ultimate strength, that is your permissible strength, will not equal be to your yield strength. Okay. If you are from simulation background, you know that for static study, we use yield strength as our permissible limit. Okay. But in fatigue case, this is not the case. Okay, we can't take yield strength as our ultimate strength or our permissible strength, because here you can see, okay, for same loading condition, okay, if I apply this load for 8,000 cycle, okay, this is one cycle. Okay, I have multiplied by 1,000, so I have applied 1,000 times this cycle. So here you can see I have a gain around 43% damage at this part. Okay. So here you can see at very low load. Okay. At 100 Newton load on static analysis, I have seen that my part is overly saved. Okay. I got the 43 times more safer body. But when I doing the fatigue analysis, I can comes down to that my part is going to be fail after 2000 after the 16 the triple zero. Okay, that is after 16,000 cycle my body is going to be fail. Okay, so to analysis for doing this type of analysis, generally we are go for experimental data, okay. But before going to experiment, we can also do that type of simulation in SolidWorks simulation in fatigue analysis, okay. So this is a very good example where you are going to perform a fatigue analysis. So if this is the SN curve data, so who are from this vibrating industry, that the body is under the vibration and dealing with that type of stuff, so they know what is SN data, okay. So generally the SN data curve, if I have this accurate data, I can say that you can predict almost 90% of your failure, okay. So whether my body is going to fail, you can predict with an accuracy of 90%. But if you have the correct SN data, okay. So this is one another example. So this is a basketball ring, okay. So what I have done is my basketball ring is fixed here, okay. So for my static analysis, my body is overly safe, okay. But when I have done my fatigue analysis, you can see the actual scenario that a basketball player going to basket here. So at that time, it has one vibrating load, okay. This type of load is going to be applied on this body, okay. So up to which cycle my body is going to sustain. So to predict that, we do a fatigue analysis. So here you can see, so up to 7,000 cycle my body is going to be safe, okay. After 7,000 time, I may get uh, the damage of around 142%. That is, my body is going to be fail after 7,000 cycle, okay. So not only for this type of example, but also when you are doing with rotating machineries, if you have ball joint, okay, some other industry like airplane wings, okay, that is also going to under wind load, okay. And wind load never going to be a constant value, it is always going to be a time dependent value, okay. So then we have offshore platform, that is suppose we have any geometry, suppose we have any wind turbine at my offshore, okay. So I want to check what are the wind loading applying on it, okay. Also ship, vehicle axis, bridges, okay. So these are the examples of fatigue analysis on which you can perform fatigue analysis, okay. Then we have linear dynamics. Okay, so what is linear dynamics? In static, we have seen that our load is not does not depend with time, but it has a constant value. Okay. Now in dynamic loading, what we are going to do is my load is also varying with respect to time. Okay. So do not confuse between fatigue and linear dynamics. Okay, in fatigue analysis, we are introduce omega, that is frequency we are introduced, but in linear dynamics we are introduce time-based force. Okay, so for if your body is subjected to certain frequency, then you are going to perform fatigue analysis, and if your body is going to subject to uh, frequency based force, okay, that is changes with time, in that case you are going to perform linear dynamics, okay. So in linear dynamics we have three subdomains. First one is harmonic, second one is random, and third one is response spectrum, okay. So what is harmonic vibration? So harmonic, it suggests that it it may going to be a sine curve, or it may going to be a cos curve, okay. So here you can see my load is going to be follow this fashion, that a sine omega t plus phi. So here is my frequency, my time step for up to which time I'm going to apply this load, and that is a phase lag, okay. So what is my phase lag, okay. So here is the general distribution how my harmonic load is look like. Okay, so it is performed like this. Okay, so yeah, any body that is under a harmonic vibration. Okay, so if you have any machine element, okay, suppose I have one motor mounted on a stand. Okay, and when the rotor is rotating, if there is an offset between the CG and the shaft, okay, that is, suppose this is my rotor, so here is my CG of rotor and this is my shaft. Okay, so if there is some eccentricity is present, that is E is my eccentricity, so what happen is that here is my stand, okay, my bottom stand. So what is going to be happen is, here I can feel that here my body is subject to harmonic vibration. Okay, so here you can imagine, suppose this is my, when this part is up, okay, then there is a minimum load. Okay, so it is going to be load like this. Okay, so this body is going to be up and down like this. Okay, so this is one example of harmonic vibration. Suppose you have any body that is mounted on any stand or something, and if there is eccentricity present in your model, okay, so at that time you may face that the body is under harmonic vibration. Okay, so now here is my harmonic vibration. Okay, so here I have one example. This is my AC cabinet. It is not look like AC, but consider it is an AC. Okay, so I have generalized this as one AC, and I have mounted that AC on two beam platform. Okay, and here I have fixed it here I have fixed it here, fix here and fix here. Okay, and now I want to check that whether my body is going to be sustain that load or not. Okay, so what type of loading I have applied? So here you can see, so not only in cyclic fashion, you can also apply load like this. Okay, suppose I want to apply it for a quarter cycle. Okay, not full cycle, a quarter cycle. Okay, so this is my quarter cycle, but in sine curve there is a gradual change, but here I have a sudden change. Okay, so you can also apply this type of sudden change also. Okay, so I show you how my body is going to be vibrate here. Okay, so here you can see. So for quarter cycle, this is the case. Okay, so this is about harmonic vibration. Okay, so in harmonic vibration we have limitation that you have to give your loading condition as sinusoidal curve or a cos curve. Okay, but that is not an always case. Okay, suppose I have one example here. Okay, this is my body. Okay, so this is my electrical component. Okay, so here it is attached with another body. Okay, here it is attached with another body. Okay, so what happen is this, that this body is vibrating. Okay, so due to this body is also going to be vibrate. Okay, but this vibration may not, or maybe it's going to be a sinusoidal. Okay, so for sinusoidal we can do harmonic analysis, but we don't have any idea that how is going to be the vibration pattern. Okay, so for that we have another module called random vibration. So in random vibration you can perform any type of vibration. Okay, suppose my vibration is like this. Okay, so this type of vibration is that, and you want to check whether my body is going to sustain that vibration or not, so you can also perform here. Okay, so to perform here you need to get this vibration data. Okay, so once you have that vibration data, you can automatically import that file into SolidWorks as a load, and software automatically predict that whether your body is going to be fail or not. Okay, so here is the example. So here you can see, okay, uh, due to vibration, you can see a clear wave is generated, okay. So here you can find that due to vibration, my bottom plate is going to be fail first, okay. It has highest deflection. So by this, you can also measure the random vibration phenomena, okay. Then we have response pattern phenomena. Okay, so what is response pattern phenomena? Okay, so generally we have see that there is two type of excitement is there. First one is in body excitement, and second one is external body excitement. Okay, so in body excitement, as I told you, random vibration, you can perform that. Okay. For external body means suppose we have an earthquake phenomena. Okay. You have one body placed on the earth, and there is an earthquake. Okay. So due to earthquake, what are the damage your body is going to get? So you want to check that. So you can check that also by response spectrum. Okay. Also, suppose my car is moving on a highway. Okay. And there are many holes and bumps that are there. Okay. So that is also one type of phenomena. Okay. So that is also you can perform in response spectrum. Okay. So here I have one PCB chip here. Okay. So here you can see I have one PCB chip here. Okay, so you can see that this PCB chip is mounted here. Okay, I have mounted this PCB chip with my original machine. Okay, and due to earthquake, my whole body is vibrating like this. Okay, in random fashion. Okay, so I want to check how my this body is going to be performed. Okay, so here you can see. So here you can see that my this part is failing first. Okay, so the reason behind is I have fixed my part here. So from that end to that end, my part is perfectly fixed. Okay, my this part is not fixed very tightly. Okay, so here you can see the deflection is highest. Okay, so here you can see the displacement is highest. Okay, so this is how you can perform a spectrum analysis. Okay, then we have our next segment, that is, yeah, sorry once again. Okay, uh, just a second. Okay, okay. So this is about our response spectrum, and then we have non-linear analysis. Okay, so what is non-linear analysis and linear analysis? Okay, so the major difference is you can predict from stress strain diagram. Okay, so here I show you that up to the elastic limit. Okay, so when you have studied your stress strain diagram in our engineering study, that we see that at B point we have our elastic limit. Okay, and that is not that is our yield point. Okay, so in static analysis or all linear analysis, what we are doing, we are choose yield strength is our ultimate strength. Okay, and we perform that. So one major scenario I want to highlight is up to the elastic limit, sorry, up to the yield point, you have your elastic region. Okay, so, and after that you have your plastic region. So what is the difference between elastic and plastic? Okay, so just consider our rubber band. Okay, so rubber band is elastic, that if you pull it and you release it, it automatically gain to its original shape. Okay, so that is called elastic. And plastic means, suppose you have one polythene bag. Okay, you have stretched it, and if you release it, it never going to back its original position. Okay, so that is called plastic. Okay, so to differentiate between elastic and plastic, we have introduced the yield point. Okay, so if my model is below the yield point, okay, then my body is under elastic limit, and if my load is above yield point, that is in plastic region. Okay, so for plastic regions analysis, we are going to perform non-linear analysis. Okay, so in non-linear, here you can see if I follow the plastic region, then uh, if I follow the linear analysis, so linear analysis, what is said that my stress is directly proportional to strain. Okay, so if I follow my linear limit, linear elastic studies, so it going to be performed like this. But in actual case, my non-linear is going to be in this fashion. Okay. So to predict my actual phenomena of non-linearity, we have one segment called non-linear analysis. Okay. So in nonlinear analysis, I have one example. Suppose this is an hose pipe bend. Okay, so now I want to check that I want to deform it. Okay, so what are the stresses is going to be produced? So if I want to check that, so here you can see. So here you can see how is going to be bend. Okay, and what are the highest stress area. So here you can see those are my highest stress area if I perform a non-linear analysis. Okay, so this is one example. I show you another example like our, suppose I want to bend a seat. Okay, so for bending my seat, okay, I'm going to be use one punch and die. So on die, I'm going to fix my seat, and by punch, I'm going to apply that impact load. Okay, and I want to see how my body is going to be deformed. Okay, so that deformation is plastic deformation, not elastic, because once it is deformed, it never going to its original position. Okay, so this is a prime example of non-linearity. So here you can see how my non-linear analysis is going to perform. Okay, and what is the stress value are going to in introduce in my seat body part. So here you can also predict at which part my stress is high and at which state my stress is high. So here you can see at this stage it has highest stress developed here. Okay, so suppose this stress is above my yield point limit. Okay, then that may be a chance that my seat is going to be tear out from here. Okay, due to shear stress. Okay, so that type of analysis also you can do in SolidWorks. So non-linearity has a wide spectrum to do all this type of analysis. Okay, so then we come to a last topic of the day, that is thermal analysis. Okay, so this all are static analysis. Okay, so static, non-linear and dynamics we have seen. Now we have seen one thermal analysis. Okay, so SolidWorks simulation perform thermal analysis for all domain. Okay, whenever I tell thermal, that three pictures come into my mind, that is conduction, convection and radiation. Okay, you can perform all this simulation in your SolidWorks. Okay, so if I want to check how my conduction is phenomena is going to happen, how my convection is going to be happen, if I apply one radiation phenomena, that how it is going to be performed. So I can capture all the phenomena in thermal analysis. So thermal analysis have the conduction, convection and radiation heat transfer problems. Okay, and it have two problems. One is time dependent, that is transient, and another one is our steady. Okay, that is independent of time. Okay, so this is one example of steady analysis. Okay, so what I have done here is that this is my spark plug. Okay, so my spark plug has different types of loading, heat load. Okay, so what are the loads? I tell you, first one is this is my lead. Okay, from where my spark is generated. So it has around temperature of 700. Okay, just random. I take this. Okay, 700 Kelvin. Okay, and this body is in a contact with coolant. Okay, so I have predict that here my heat convection. Okay, my convection ratio is around 25 watt per meter square. Watt per meter square Kelvin. Okay, and this one is my remaining part, that is the outside body, which is directly in contact with environment. And suppose my environment heat convection value is around 10. Okay, 10 watt per meter square Kelvin. So by this loading, how much my body has the temperature introduced in the body, I want to check. So that is easily done by thermal analysis. So here you can see that this portion at highest temperature, okay, around 812 Kelvin temperature. Okay, this this and this also have same phenomena, and this is the part which is the very far from my heat source. Okay, it has very minimum temperature. So here you can see, you can exactly capture the phenomena. Okay, second, I can show you another example of heat sink. Okay, suppose I have one heat sink here. Okay, so what I have done here is my heat sink is fixed here. Okay, and here I have a heat load here. Okay, suppose my heat sink is connected to a chip. Heat sink is generally used in your CPU and where you any your transistor. Okay, so the main purpose of heat sink is to reduce the temperature of parent body. Okay, it is function, it function is like fins. Okay, so here my heat sink is connected to a parent body, and it has some heat load. Okay, suppose it had 100 watt load is applied already. Okay, so I want to check how my temperature is transferred to the environment. Okay, so here I have introduced the environmental heat convection value. Okay, so I want to check how my environmental phenomena is, sorry, how my body has the temperature, different temperature, different location. Okay. So to perform that analysis, we have steady state thermal analysis. Okay. So here I show you. So this is my temperature distribution. Here you can see. So the upper part, as we can see, the upper part is the highest temperature, because the purpose of heat sink is to transfer temperature as soon as possible. Okay. So here you can see that that is the, due to high conductivity, the same temperature of the body is going to be introduced on the upper face. Okay, and here we have the largest uh, sorry, I can say largest of face exposure to environment. So we have very low temperature here. Okay, so here you can see how my temperature is going to be introduced. And also one another thing I forgot to tell you, that you can also integrate your thermal analysis with your static analysis. Okay, static and fatigue analysis. So what is that? Suppose I have applied this load. Okay, now I want to check, due to this thermal load, what is the stress developed in my body, and is what are the thermal displacement due to this temperature I want to measure. So to do so, you don't go for any separate study. Okay, you just integrate this thermal study to your static study or your with frequency or fatigue study, and automatically software will take this result as input of that next study and perform the study analysis. Okay, so here this is the example of how the stress is going to be produced. Okay, so here you can see I have directly took data as my input data, and here you can see how my body is going to be perform under stress, under thermal stress. Okay. Similarly, if I want to check what is my displacement, okay, due to this temperature. So here you can see. So this has the maximum deflection. Okay. So that is have around you can see 0.25, 0.3 mm, 0.03 mm deflection is there. Okay, so if you have arise one question that there is a 0.003 value of deflection, that how this body is behaving like a very large displacement. Okay, so I have turned on the deformation result. So you deformation result is nothing but your scale result. Okay, suppose I have stress of 1000 Newton. uh, so if I apply one scale, suppose I scale to that to 10 times, okay, so that becomes 10,000, okay. So why I have applied this scale module? Because you can see the phenomena, okay. If I turn off this deformation scale, so you don't going to be uh, see that this how this body is going to be deflect, okay. So to perfectly capture this deflect, I have on the deformation scale, okay. So this is all about the static simulation. Okay. Now we have time dependent simulation. Okay. Suppose I want to apply that my simulation is time dependent. Okay. That is how my body is going to gain the steady state condition. Okay. So in our engineering study, we have seen that when our body is subjected to any cold environment, okay, so there is going to be a phenomena called lump analysis. Okay, so lump analysis tell us that your body is going to cool at exponential rate. Okay, so here is the same situation. Okay, so I have performed the transient analysis, so you can see that. So here my body is firstly at very low temperature. Okay, so as my temperature increases, my temperature is also increases. Okay, and after certain second, it has achieved its stagnation state. Okay, so after that, my time is my temperature is not varying with time. Okay, so this type of analysis also you can predict, and from that you can also find your transient tensor graph. So this graph is between temperature and time. So from here you can say that around 2.42 second, okay, my uh, my body has achieved the steady state. Okay, so after that if I vary the time, my temperature is not going to change. Okay, so this is a very important phenomena when we are designing a heat sink. Okay, so our main goal is how this this time, the minimum time, okay, it is going to be reduced. Okay, so as low is your this steady state time achieving the steady state temperature, so that is going to be your base heat sinks. Okay, so this type of simulation you can perform in SolidWorks simulation. Okay, so this is all about how SolidWorks has different modules and what are the simulation you can perform in different modules. Okay, so this is all about from my side. If you have any query, please comment in the chat box or you can ask. Okay. Anyone have any query regarding to any module? Okay. Here I have show you all the modules. Okay. If you have doubt in any module or you have one your problem, okay, if you are from an industry and you are designing any model and you want to check which type of study I can perform on your body. Okay. So anything.
Hello,
Okay. Ah, sir.
Penny.
Ah,
Penny sir,
yes.
I have a question regarding to the result comparison between the ANSYS and SolidWorks.
Okay.
If I perform one static study in SolidWorks simulation and the same condition I applied same load in same fixture in ANSYS, is there any result difference between two?
Actually, that is no. Okay, so I tell you
Okay,
why. Because both SolidWorks and ANSYS are going to perform simulation based on FEA theory, not ANSYS. Any simulation software you take, they are mainly based on FEA module. Okay, so FEA module have same problem. The how to solve any FEA problem that has its own steps. Okay, so if
okay,
you want to solve any FEA problem, you must go through that steps only. Okay, so
okay,
only
okay,
difference is that the meshing technology. Okay, so how my model is going to be meshed. Okay, and how my solver is accurately capture the problem. Okay, so
okay,
that are the more scenario. So according to that, you are going to face difference in the actual value and in one software and another software. Okay.
okay, okay.
Uh,
Thank you.
okay. Okay. Any other question? That's a good one. Ankit, you can also perform. I can say you suppose apply loading condition on a cantilever beam. Okay,
Okay.
cantilever beam on SolidWorks and cantilever beam on ANSYS. Okay, I can say you that you are going to get almost same value. Okay, that might be a difference of 10 to 20%, but I cannot say that ANSYS is accurate or SolidWorks is accurate. You must go for the experimental analysis also. Okay, so by doing experimental analysis, you can verify that my ANSYS results are more accurate or my SolidWorks results are more accurate. Okay, but only difference between ANSYS and SolidWorks I can say is the user interface. Okay, so if you want to do any analysis in ANSYS, okay, so you can design any model, any complex shape in space clamp. Okay, if you ever use space clamp, you can see that it is more difficult than AutoCAD. Okay, so you can design any complex geometry. And second thing, in ANSYS, what you are going to do is you first uh, design one into any CAD module, okay, any other CAD software. Then this model you are going to save as Parasolid IGS or STEP, and that file you are going to import in your ANSYS study. Okay, then after you perform ANSYS study, and once you perform your ANSYS study, you found that my body is going to fail. Okay, there is requirement some modification. So to do so, you again change that modification in your CAD module. Okay. Then again, you want to check whether these changes I have done is safe enough or not. So for that, you again going to do same steps in your ANSYS. Okay. But in SolidWorks, the main advantage is that SolidWorks has the simulation add-in. Okay. So add-in means if I change any things in my model, that automatically bring to my change to my simulation study. Okay, so if I suppose I have add some fillet. Okay, suppose I show you uh, very okay. Suppose this is my this study I want to perform. Okay, so if I want to check that my body due to torque, this portion is going to fail. Okay, so what you are doing to your ANSYS, so you can't add fillet in your ANSYS. Okay, so what you are going to do is you are going to your CAD software, then going to apply fillet, and again you are going to save is a parasolid step, IGS and other things, and going to import as in a ANSYS and again doing for the same study. Okay, so think of your computational time. Okay, and computational time plus your man time. Okay, but in SolidWorks, what is that? It is a built-in add-in. Okay, so once I applied fillet here, and I have to just rebuild my study or run this study again. Okay, just one step, and software automatically take all that changes and give me the result. Okay, so this is the difference, and also the user interface. Okay, if you visited any SolidWorks interface, that there are steps available. Okay, so you are going to perform any study by step by step. Okay, so first check mark, first step, second step, third step, and accordingly to you don't need to go for any random step. Okay, so in suppose you are doing in ANSYS, so first you go to a module into a space claim, then you going for a name selection, then you are going for mesh, and we are going for apply in loading condition, fixtures, and post processing. Okay, so that is not case in SolidWorks. Any other question? Okay, so I have not found any question here. So here we are conclude our webinar. Okay, so thank you so much for joining here. And if still have any query, you can reach out us. So here is our mail ID, our website. You can also contact me for any change. Okay, any query you have. Okay, anything you want to know about SolidWorks or other products like CAM product. So you can reach out us. Okay, so thank you so much all of you for your patience. So we will meet next time. Okay, goodbye.